So this is Yang-Sen's inequality, right? So what does it mean? This function below here for any xy, okay? What is this? This is convex if I have a support, or this for any xy, and you can get these two if and only if. I didn't talk about the proof last time. Now I talk about proof. So this thing give you this thing, and also this thing give you this thing. I talk about just one of them. So actually it's not hard. So I start from here. So I copy this. I get this. What's next? Lambda go to here. Lambda here, and I have lambda here. So I have lambda fy minus lambda fx. This part. And the fx just go in front. So okay. What is this? Now I move this part to the other side. Now I have this. Okay. Now I move lambda to the other side. Now I have this. Now you see I want to do differentiation. So I have this thing. Now I put it in this direction. Now I get this. What is this? This is lambda. No lambda. No lambda. So limit lambda. Limit lambda. This is directional derivative. So I get this. So fy larger. fx. This whole thing is directional derivative or Gatot derivative or Frechet derivative. Okay. So I get this easy. What about the other direction? The other direction is now I have this. I create two of them. I add them up. By creating this, then I get this. That's it. Nothing fancy. Okay, this one is even easier. So now I'm going to talk about the detail. What the heck is this? So red is below green, so this is convex function. But these two lines, the red and the green, give you a gap. This gap can be a function, and this gap is now called Bregman divergence. So I call it B. So what is this? You can think of it as the area of Taylor series. Why this is called divergent? Because this is always larger than 0 and always equal 0 if I have y equal x. Because when I have y equal x, I am at this point, the gap is 0. Why this is not a distance? Because it does not satisfy triangle inequality or symmetric. I don't remember which one. But anyway, so this is the idea. And this thing is many years ago, okay? But okay, we don't care. Then this is the idea. So what is this? Well, this is basically this thing, convexity. I just move this to the other part, then it's a function. So this means this exactly is convexity. But now I fix the PQ, and that's it. So you can think of P is a point, Q is also a point, but Q is a reference point. Because look back here, Q is the gradient. This is fixed. So you can think of this thing here. If I have here, this is the Q. Okay, this is the Q. And I find the gradient of the Q, and I move along the P, which is here, with respect to this point. Because every time if I change the tangent, I'm with respect to this particular Q. So this is Q dependent. But anyway, so I have this thing, and this is convexity. I just said, right? And then here's a funny thing. This is saying I have something F, right? Something F. What happens if my F is 2 norm? So let's do it. So this is definition. So now I have this thing F. So this is square. What is this? This is revision. X. Then how do I differentiate it? This is basically dx squared. Then 2x. Okay. So 2x. So that's why 2y because it's on y. Okay. And then I have this thing. Okay. Nothing changed. Now I have 2xy and then inner product 2yy. So I have 2yy. And the 2yy is positive. With respect to the minus sign, I have 1 positive. What is this thing? Okay. This is wrong. This is xy. Okay. Then I get this. This is thing. So therefore, distance is Bregman divergence of norm. Okay. Nothing special. But now this is the fun part. If I have x log x, this is called Shannon entropy. And now I do this d dx. So this is, you know how to do, right? D the first guy, keep the second guy. So you have log x. And then d the second guy, keep the first guy. D the second guy is 1 over x. 1 over x and x give you 1. So you have this. Okay. Now I want to do the Bregman of this f expression. This f is x log x. So this f is x log x. This is on y. So y log y. Okay. No change. This is x minus y. So x minus y. This is inner product. So I have component. This thing is each of the component take gradient. So I have log x plus 1 each of component. But now we are on y. So I have log y each component plus 1. Okay, no problem. I have this. Now what? Simplify stuff. This part I keep here. This part I look at the thing that is common. I have y log y. This one I have y log y. Look ahead. Y log y. And then what? This negative and this negative become plus. And it cancels with the negative. So y log y is gone. So I don't have this term. I don't have y log y. I just need to look at this thing, multiply x by this, and this is negative. So I keep negative. Okay. Now I have this whole thing. What's next? X go inside. So x log y and x. So I have this thing. This thing, if I restrict myself, this is inside the unit probability simplex. That means these are probability. Then probability sum to 1. This is 1. So I have this whole thing. Now I have x log x minus x log y. take out the common factor, have this log A minus log B is log A divided by B, so I have this is called KL divergence. So in other words, what is KL divergence? It is this thing where my green is Shannon entropy. So therefore, KL divergence is the Bregman divergence of Shannon entropy. That means what? That means this is convex or something is convex. Alright, now this is simple. Let's look at matrix version. So I have x log x, well this is just this. Now I have trace of x log x. What is this log? This is matrix log. So it is a Taylor series on log. You can have a crazy expression on a matrix logarithm. Of course, we assume all this is positive definite. Otherwise, you cannot take log. Okay. Then now I have the same thing. What is the same thing? I just do this fx minus fy inner product between gradient y x plus y. So this is the expression. And because we are talking about everything on matrix log, just recap. You have trace of something. X is positive definite. That means you can have eigenvalue decomposition x lambda v lambda v. So you have v lambda v something like that. Trace, this guy can go here because trace ABC is trace CBA, CAB. So I can move this up or I move this down. So VV transpose kill each other. So I live with what? I live with just eigenvalue. Then this thing is the same. Then I will have log of something positive. Log of something positive means it's the same thing. It's just this thing because it's diagonal. Okay. Then I can do something similar. Then what? This is matrix version. Fun fancy name called von Neumann divergence. It's just Shannon entropy. Okay. Then what? This is the same idea. You get the same expression here, but we now have this version. And then what? These two things I can come up with what? Log, right? This looks exactly like KL divergence, but for matrix. Of course, you need a TR here. Okay. Then what's next? If I have this funny thing, I get something like this. Okay, this is wrong. There should be determinant. But anyway, okay. So you get something similar. So these are all what? Example of this. Then you will ask, why talk about this? What's the heck? Here's the idea. Actually, I talk about this somewhere in the gradient descent. So remember, I want to minimize this. How do I minimize this? At iteration xk, I build this as f of xk plus kk, and then what? And then I have a quadratic term, right? Quadratic term x minus xk, and then here I have alpha I, right? Step size I, and I need to make sure my alpha is larger than the Hessian. Then this is above my function. Good. Here's the thing. What if this funny thing is absolute value? If this thing is absolute value, come on, you cannot do this. There will be some function that you cannot do this. This kind of funny function usually have a funny geometry. In other words, this is saying that you have a quadratic upper bound. But what if the function is a diamond or not regular diamond? It's like this. Yeah. So this part is very sharp. This part is not so sharp. Or let me draw better. Maybe the geometry is like this. Okay. Yeah. The geometry is like this. Yeah. Something like this. Okay. Then this is bad. This does not fit this. If you remember the argument, then gradient descent will be like this. Never go to here. Very slow. Then what to do? This thing no more. We replace it by the B. Then we have a new series of algorithm called mirror descent, and it is just gradient descent by replacing this thing by the B. So what I talk about, let me go back. I want to do this. I just talk about this thing give you this thing normal cone, right? This is on this part. This Bregman divergence is on what happens if this F is not circle, it's not sphere. Then we use better geometry by the B, by the Bregman divergence thing. Okay. So these are all the possible cases. You cannot have other thing, right? So what will be the other thing? The other thing will be these two appear at the same time. So it is, I just give you example. Okay. Then this is an example. Minimize the absolute value of one norm, non-differentiable. So you need this subject to crazy constraint here. Then you need both of them combined together. Then in this case, you will need this, but even more general. So this is basically the idea. Is we already know how to do this for simple f. Then what we do next? Add a constraint here, make it more complicated, or add something. That's the content next few days. And the central idea is the same. Okay. So these are formula. We don't care. Okay. And then this is duality later. So here is the idea. So you have this, then it gives you this. This is convexity. Convexity naturally gives you something like this. That has nothing new. And what is this thing? This thing is useful for f that is not this. Okay. For example, in some application, you want to minimize this instead. X larger than 0. Let's say you want to minimize this. You cannot do gradient descent because first of all, this is not differentiable. Secondly, you have non-smooth. You cannot even do proximal gradient. You have to do something else, but later. So these are the details.